Welcome back to the next part where I finally finished this fin assembly. In the last video I covered making the fins, and in this video it's all about the brackets. Making the mounting holes and then finally assembling the fin can. If you need additional background on this assembly, then I suggest that you jump back to the previous video where I covered the core design concepts. I received so many comments that say, oh, you should just 3D print that. So I briefly interrupt this broadcast to talk about the sponsor of this video, PCBWay, who kindly supplied a fully 3D printed aluminum version. PCBWay are great since they allow you to simply upload parts to their easy to use website, and then your part of choice is manufactured and sent to you in just a few days, opening up a whole world of possibilities for fast, easy prototyping in a wide range of materials and manufacturing techniques. For example, in their 3D printing services they include materials, but not limited to resin, nylon, PLA, ABS, as well as aluminum, stainless steel, and even titanium. They provide all sorts of small-scale manufacturing services for makers and hobbyists, such as PCB prototyping, 3D printing, CNC machining, and even OEM services. There are so many processes you can use to make parts from different materials. So head over to PCBWay with the link in the description to get started making parts for your own projects.
Then I've also explored using Hewlett-Packard's MJF or multi-jet fusion technology to 3D print this assembly. A big shout out to Hewlett-Packard who partnered with me on this project as well. But more on both this 3D printed version as well as the aluminum 3D printed version a bit later. Let's dive in and make the aluminum brackets. I was able to fly Project Rosefire one more time at an event in Eastern Washington on an experimental K568 that uses a solid propellant known as Methalox. This propellant produces an exhaust that looks exactly like a liquid Methalox motor, which is this beautiful purple pink. This was another successful flight to around 8,000 feet, and this time a subsonic flight to stay within the waiver. I was also able to test my new minimum diameter launch tower. Anyway, let's dive in and actually make this bracket. The approach to machining this bracket is effectively a copy of what was done to make the fin, as it relates to machining setups and work holding. So I apologize if some of this sounds repetitive. Okay, since I'm using a 3-axis CNC mill, I'll need 2 setups or cutting operations to complete this bracket. And I'll start by reviewing the machining setup for the first side milling operation. Let's start by looking at the machining setup for the first side operation. Again, similar to how I approached the fin machining setup, I like to define my stock as a solid object. So I model the stock relative to the part I am about to make. Next is defining the work coordinate system, and I use a stock box point. And again, I know this is not the best strategy, and I should really be referencing a fixed point on the mill, such as a point on a vise. Alright, so onto the toolpaths for Op 1. And this is going to be a high-level overview, and I'm not going to go and review all the detailed toolpath setups at this point. It's just an overview. Starting with a facing operation, using a 2-inch fly cutter and taking 10th thou just as a cleanup. The next thing I do is to cut a reference pocket. As mentioned in the fin machining video, this might be controversial since there's potentially a different way to approach this. However, this reference pocket is used to accurately reference machined XY surfaces when locating the XY0 coordinates for the second side machining operation. I know that sounds convoluted, but you'll see how I use this pocket during the setup 2's configuration and when I find XY0 on the CNC mold. Then we're on to the initial roughing operations, removing the stock to expose the bracket contour and the rough surface profile. Next up is the finishing operations, where I profile the bracket surface with a ball end mill using a combination of flow and scallop toolpaths with a 20th step over. After that, I cut the outside contour, and I also cut tabs to prepare for Op2, basically creating a secure way to hold the bracket in place for that operation. I will mostly show the results after each milling operation, since it's really hard to record inside the mill with flood cooling running. Starting with the raw stock, and here I'm finding the XYZ0 coordinates. The first cutting operation is the face cut using a 2-inch fly cutter and just taking 10 thou as a cleanup. Next, I cut the reference pocket and I started drilling a hole, and this hole will speed up the next boring operation. I also drill another hole to help with coolant evacuation once I start clearing stock. Then I bore the pocket with a 1/4-inch end mill. And then onto the first clearing operation, where I expose the brackets, rough contour and surface profile. At this point, I'm basically sneaking up on the surface profile, starting with a 3/8-inch end mill for a really rough finish. And then I move on to a 1/4-inch end mill to further refine the surface profile. And then finally fully forming the surface profile with a 1/4-inch ball end mill. And here's a quick time lapse showing this whole milling operation. And here's the result after the surface profiling. The 20th step over created a great surface finish. There's some rub marks where the swarf was pulled into the cut, and I should probably just run a stronger coolant stream. And the final operation was cutting the edge contour and tabs. And we are now ready to flip the stock for the second machining setup. So this is what we have after the first cutting operation. As you can see, half the bracket is still stuck in the remaining stock. Since the bracket is secured with the edge tabs, I can clamp this in the vise and finish the bracket's bottom surfaces. But the problem again is the final contour cut. It'll just go flying if I do not secure the bracket onto something solid below. So to prevent the bracket from flying off, I will use the same work holding strategy that I implemented with the Fin's second machining setup. where I use a mirrored surface plate. Again, this has to be a mirrored plate since the first side of the bracket has the aerodynamic profiles. It is not flat, and the mirror plate will ensure that there's full contact between the bracket surface and this work holding plate. I then super glue the bracket onto this mirror plate to ensure a really strong work holding setup. But before I do that, I prep the two surfaces using powder coat tape. This acts as a barrier to protect the surfaces from the super glue, making it a lot easier to clean up, as well as making it a lot easier to separate the two sections at the end. It also creates a really strong bond between the two surfaces compared to gluing these parts together directly without the tape. Alright, let's dive in, starting with the machining setup. Again, the stock is defined from the previous setup and I use continue rest machining. Onto the work coordinate system, and things get a little strange again as it relates to defining the work coordinate system and specifically the z-axis. First of all, I create a sketch that uses the reference square from op1 to define the XY axis intersection. For the z-axis, I also want to reference a machine surface, but at this point all z machine surfaces are hidden and there's also no flat surface on the bracket's first side. I cannot really reference the stock surface since that is not reliable. So I'm back playing the game of relative coordinates. I again opt to use a flat surface on the mirror work holding base, but this time I deliberately had to make a flat surface on this plate that is in the same z-axis plane as the top bracket surface from op1. This flat surface is then accessible through the reference pocket I cut in operation 1. I know this is really convoluted, but it works really well in the end. Then I create a sketch in this flat surface plane, and this will define my z-axis reference or z0. Then the work coordinate system origin for operation 2 can now be set at this x, y, z intersection. Okay, so onto the toolpaths for operation 2. I start with roughing out the bracket's center surface profile. Then I finish the center surface profile with a flow toolpath. Next, I cut away the contour tabs, since at this point I need to remove the excess perimeter stock. And you'll see why I need to do this once I show the actual machining. Then I'll rough out the two side profiles, and then finally I will finish these side profiles with a ball end mill. Okay, so onto the milling, and again I will mostly show the results after each operation. Starting with finding X, Y, Z0, with Z0 being located on the mirror plate, and then using the reference pocket to find X and Y0. Touching off the first end mill on the tool setter, and then straight into the first roughing operation. And then the results after this op. You can see the rough stepped surface profile. And I finished the surface profile with a ball end mill using a 40 thou step over. And you can see the results. Not the best surface finish, but it's okay since this surface is completely hidden in the end. And then on to removing the tabs that are holding the bracket in place. And here you can see that the tabs are now removed from both of the side profiles. And then I need to remove the excess perimeter stock. Since I need to add a custom clamp to securely hold the bracket for the next side clearing operations. The clamp is an extra layer of work holding security since I just removed the tabs and I do not want to just rely on the super glue. Here I'm installing the clamp and you can see that it's profiled to conform to the bracket's surface profile. Yet again another custom part that I needed to create. Next is roughing the side profiles, creating a rough stepped surface finish. And here the first side is complete, and then onto finishing the second side. Then the final offers to profile the surfaces with a ball end mill, and this time using a 20,000 step over. This is the final result, and now I just need to separate the bracket from the work holding plate, which can be tricky since it's relatively fragile at the moment. And this is what I'm left with. The bracket is pretty well glued onto the plate at this point. Onto separating the parts, and I found that using heat to break the superglue bond works the best, since it's really hard to get acetone between the layers. Then it's just a matter of prying the bracket off and the powder coat tape working really well to protect the surfaces from the glue, making the cleanup really easy. So final dimensions. I was shooting for 32 thou, so I'm very happy with the final results. The additional 5,000 is likely due to the powder coat tape affecting the Z-axis and me just overcompensating. But a little bit more here does not hurt at all. So making the holes, and this turned out to be a bit of a nightmare the first time I had to do this. So let me explain. If you saw the second video where I made the forged carbon version of this assembly, you'll remember that I had to make a special work holding block to effectively orient the bracket at a 45-degree angle to enable me to drill and bore the mounting holes. And I will use the same setup for the aluminum bracket. The biggest problem was needing to source an extra long 8-inch end mill that would enable me to reach down into the holes without crashing the collet or spindle into the bracket due to this 45-degree angle. Using an extra long end mill to bore out the carbon fiber was really easy because it is a relatively soft material. Boring the holes in aluminum is a whole other story, since such a long end mill will just create a lot of chatter. So I sourced a slightly shorter version, but faced the same issues with chatter. The problem was that the end mill shaft should have been thicker and only tapered down at the tip with the smaller cutting radius. So the only way around this chatter issue was to slow down the cutting feed rate to 5 inches per minute, agonizingly slow, and then there was the 48-hole multiplier. I think the whole boring operation took like 4 hours. Crazy, but I could not risk pushing the end mill any harder since it's the only one I had at the time. and I really needed to finish this bracket in time. To solve this problem, I'm ordering a custom end mill from Harvey Tools where I can design the tool to the exact dimensions, and that'll allow a thicker shaft and still allow sufficient clearance, and ultimately that'll allow me to just go faster with the boarding operation. Here I'm installing the bracket in this work holding block and then adding yet another custom clamp, and this clamp was shaped to conform to the bracket surface profile, and I had to cut a side relief into this clamp to give more tool clearance. And here are all 4 brackets and fins ready for installation. This is the first dry fit, and it's a matter of aligning the brackets and fins and then installing the bolt and barrel nut combinations. For the final assembly, I'll actually epoxy the whole assembly in place, and I will show that process in my next video, or one of my next videos where I'll cover the full end-to-end build process for this rocket named Project Rosefire. And here it is, the final assembly, and it looks really fantastic. Developing this was a 1.5-year journey, and I learned so much during this time. This turned into an awesome product, and I've received so much amazing feedback from the high power rocket community. I was doing some work with the team over at Teleraves Aerospace, who are developing an almost fully 3D printed fixed wing VTOL drone and exclusively uses HP's MJF technologies. They introduced me to HP, who partnered with me on printing various prototypes for this fin assembly, and I ended up modifying the design specifically for 3D printing, strengthening the design in certain places. This is the first semi-production MJF printed version, and I'm confident that this assembly will withstand subsonic flights and potentially supersonic flights as well. I was hoping to test this version at a recent high power launch, but the weather did not allow for additional flights during the waiver period. A little background on HP's MJF, or multi-jet fusion technology, and it really represents the gold standard for moving beyond simple prototypes into functional, flight-ready aerospace components. Unlike FDM or SLA, which often suffers from layer line weakness or material brittleness, MJF utilizes a unique powder fusion process that creates isotropic mechanical properties, ensuring parts are equally strong in every direction. It is a critical requirement for components facing high-stress aerodynamic loads. As mentioned, PCBWay kindly sponsored this fully 3D printed aluminum version. It was really easy to work with them, uploading the STL file, selecting the required manufacturing and material properties, and then a couple of weeks later, the part arrived. This assembly was printed as a single unit rather than a modular assembly, just to showcase the art of the possible using SLM or selective laser melting 3D printing. The SLM process uses an aluminum alloy known as AL Si10Mg. The AL is for aluminum, which makes up about 90% of the material. The SI is for silicone, which is about 10%, and is critical for the SLM process because it increases the fluidity of the melting pool. And then magnesium, which makes up about 0.4% and enables precipitation hardening. This thing is a unit. It feels really strong and stiff, and I will have no problem flying this assembly at any speed possible in a 3-inch airframe. It was also really easy to mount on this carbon airframe. Unfortunately, I wasn't able to test this assembly in a real test flight, but hopefully we'll be able to do so in the future. So I'm back in my workspace, and a number of months have actually passed since I've finished this assembly, and during this time the rocket has flown twice, once at Blackrock up to 18,000 feet, and this past weekend up to 8,000 feet. So I'm just going to share some final thoughts on this assembly. Okay, so let's talk about the strength of this assembly. This thing is incredibly stiff and strong, and that's just due to the nature of the CNC milling process. There's such tight tolerances between the fins and the brackets that creates this really strong radial clamp around the airframe. So there's no wiggle, there's no slop. So yeah, it's incredibly stiff. Okay, so what about the weight? Yes, it is definitely a little heavier than a pure carbon version, but in the bigger scheme of things, that additional weight is completely irrelevant. If I want more performance, all I do is add more thrust. So what's next? I would like to fly both the 3D printed versions, both the PA12 as well as the aluminum version in the near future. Then I also have a 4-inch design ready that I'll also make using the same CNC process that I just covered. My next video will likely be a short construction video on Project Rosefire, which is this 3-inch minimum diameter rocket. So my final thoughts on this assembly. It came out beautifully. It looks incredible. It's stiff, it's strong, and the last 2 flights have shown that it's capable of sustaining any type of flight. It has also been dragged through the Blackrock Desert after landing, probably for 15 minutes, and then during the last flight it also got dragged through a field in eastern Washington. And honestly, you cannot see that ever happened. And again, thank you for watching and spending time with me, and I will see you next time.